4 to 1. And it's lunchtime, isn't it? So there's 3 more slides on this section, I didn't realise that. Then we go into the next section. So we want to map a different location. Imagine we know the one-turn map at some point in S. And because this is a really important quantity, we want to figure out at a different location. Are they related to each other? Provided we know the transfer map from S to S prime. The answer is yes. And to do this, we use a similarity transformation. Now, I've stated this without proof. But if I have the one-turn map at S, and I want the one-turn map at S prime, and I know the matrix linking S to S prime, I simply take the matrix post-multiply by the inverse of M and pre-multiply it by M. That's called a similarity transformation. If you know that from linear algebra, that's good. If you don't, just know this is the way that we can move linear maps around our lattice. This is one example of what we're using from matrix theory to manipulate our one-turn map, a very central object in our theory. And because we're ages now looking at eigenanalysis and trace invariance, this kind of stuff, we won't. But that doesn't mean you can't. Textbooks will do this a lot. So let's be concrete and let's work through an example, because then we find a very, very important relationship. So let's imagine we have a matrix in some accelerator, and the transfer matrix from S to S prime is given by M equals that, in terms of strengths and distances and all this kind of stuff. We've done loads of work and we've figured this out. Let's use this to figure out how the lattice functions change from S to S prime. Because right now we can use the one-turn map in our accelerator to get beta and alpha at some point, but also alpha and beta and gamma change the position, so also we want to have a way of computing how they evolve through the lattice. And this is how we do it. So we start with a similarity transformation. So the matrix, so this is a similarity transformation. We express the one-turn map in terms of the lattice functions at the 2 different locations. So this is the one-turn map at the location S, and there's a similar equation for the one-turn map at the location S prime, where all the quantities will be primed, alpha, beta, gamma, and then the phase is a phase ratio between the 2 points. Because I know this matrix, it's just the inverse, I parameterize this matrix, I know this matrix, which is on the previous slide, and we have this parameterized in terms of the prime lattice quantities. I can just compute the right-hand side, multiply everything together, and find some expressions, and this is an exercise, for the lattice functions at point 1 in the lattice in terms of what they were at point 0, provided I know the intervening transfer map. I've not done the algebra here for you. I've put enough information on the slide for you to do that in fun one evening to write these equations, but this is the answer. So forget about how we derive it, just look at the answer. So what we have here, we have alpha, beta, gamma at some point in the lattice. I then want to know what they are at a different point in the lattice. I know the transfer matrix between those 2 points, M11, M21, M2, so on and so forth. So I construct this 3 by 3 matrix, and this tells me how alpha, beta, gamma change from point 0 to point 1. So the linear transfer map gives me these transformation equations. So if I know M between 2 points, we can transform the lattice functions at any point in the beamline. So this is how MAD works. MAD, you give it all your quadrupoles and your drifts, it computes the one-turn map, gets the phase advance, it gets beta at that point. You then, what's beta at a different point? Well, it computes the transfer matrix to that other point and just uses these equations. So if I know alpha, beta, gamma at the initial point, I can then find alpha, beta, gamma at any other point around the ring. Then I know alpha, beta, gamma at any point around the accelerator. And that's it, we've studied the linear optics. So finally, several times we've used the phase advance for one turn of the ring, or maybe over one period of repeating symmetry. It's given by that. So if I know beta is a function of S, I integrate 1 over beta between over 1 symmetry length. So it's an integral over 1 over the beta function. We give a special name to the phase advance for one turn of an accelerator. It's called the tune of the accelerator. So we call the phase advance for one turn of the ring the tune. And that's a really, really important quantity. one of the first questions you'd have of a synchrotron, what's its tune? What's its phase advance per turn? And you often see it written in units of 2 pi. So a tune of 1 would be a 2 pi evolution of the betatron function over 1 turn of the accelerator. It has a few units, symbols, nu or q. Often people give these special meaning in different contexts, like for example, q could be the 1 turn phase advance, nu could be the 1 cell phase advance, something like this. But always check what they mean by it, because they can often do funny things. There's obviously 1 tune for each plane, because we have different beta functions in the 2 planes, so the tunes can be different. So we have a horizontal tune and a vertical tune. In fact, they're never the same, for reasons we'll see coming up in terms of what's called coupling resonances. But also including the longitudinal plane. So while I've not mentioned longitudinal dynamics just yet, longitudinally is also a tune, because longitudinally also we oscillate. But we haven't studied this yet, but there are 3 tunes, there's also a longitudinal tune. So we can evaluate the tune at any point in the ring and always get the same answer. I can find the 1 turn map at this point, find the tune from it, choose a different point, find the tune. Because the tune's a global property of the accelerator, I must get the same answer. Mathematically, the trace is invariant under a similarity transformation. But physically, you can see what's going on. Obviously, I'll get a different alpha and beta at different points, because they depend on position. But the tune will always come out to be the same answer. Right, so that's the basics, the very basics of the current style of formalism. We now have to do a little bit on optics and lattice design, which will take about 20 minutes or so. Give just hear some basic terminology, basic results, and then we'll go on to studying what happens when we have errors in our accelerator. So this is kind of a slightly easier bit, 20 minutes of mostly pictures, where we're going to think about people in this building do as a job lattice design. What are they doing? So this is mostly orientated towards synchrotrons and particle colliders, and also to linear accelerators to some extent. But for example, the tools you would use in low energy situations will be slightly different. But this is what we, in a relativistic storage ring or a relativistic LINAC, this are the tools that we'd use. So we have circular machines. So what we need first of all is, if we're designing this guy, day 1 of your job at CERN, design that. Basic parameters, you need some dipoles, because the dipoles give you the bending. So practically, the dipoles, these blue guys, give you the bending in a circle. For us, mathematically, they define our curved coordinate system about which we do the expansion of the transverse coordinates. Once you've got the design orbits sorted out, we've specified the lattice, the dipole parameters, we can do them at the lattice. And this means positioning quadrupoles and other more complicated elements to achieve good focusing properties, get the tune right, get the beam sizes right, and also more complicated things we'll learn about as time goes on. So the art of lattice design is using all these tools to understand where the magnets go and how strong they should be. So here's a nice storage ring. So here it's quite a funny little shape, but we've got essentially a circulating beam. Every time where it bends, you have dipoles. So this has a nice, well-defined design orbit reference trajectory. About this, we have oscillations. Our betatron oscillations described by the beta function of the accelerator, which is a function of position, and this is determined by the k values, or where the quads are. So you can see here we have quads all around the ring. They define a distribution of k, which then gives you the solution to the beta function, which tells you linearly anyway how your particles oscillate through the accelerator. Once you've computed a beta function based on where the quads are, you can then calculate motion. You can calculate using the matrices how particles go around the ring. You can find its tune, you can find its beta functions, you can do all kinds of stuff. But life is never that simple, right? Because you have to do all kinds of things, and we'll discuss some of these things in the next few weeks. Some we won't discuss at all. You'll learn about them as time goes on in other contexts. For example, we have to get a beam into the ring. We have to inject a beam. So we need a region of the accelerator associated with injection. And that's true of all rings virtually, unless they have a source built in on a small ring, which is H- based. We also have to extract it. Say we use the ring for acceleration up to some high energy. We go in at some energy, we come out with some energy. We have to extract the beam as well. So you have extraction. We also need to accelerate the beam. I'll discuss this in 3 weeks' time, about a lecture or so, but really other courses will do more on this, like Graham Burr will talk about RF cavity design. So we need RF cavities that do the longitudinal dynamics. Our quadrupoles give us the transverse dynamics. This guy's here give us longitudinal dynamics. So we need a whole bunch of RF cavities. And then we need other interesting stuff, like, for example, collimation, to remove particles at large amplitudes that don't cause a problem on our accelerator, experiments, diagnostics, vacuum, all this kind of stuff. But the basic sequence is your dipoles and then figure out your linear optics. So here's the LHC. Here's a great example. There's the LHC tunnel. Those blue things are dipoles, 40.3 meters long inside a cryostat because they're very cold, because they're a very high field. You can just see the LHC tunnel curvature there as it goes around under Geneva in France. In the LHC, we have just over 1,200 dipoles. Each one is roughly 15 meters long, slightly less actually, but that's the magnetic length, is 15 meters. What bending field do we need? Well, we can find that very easily because the integral of B dot dl around the ring, the total bending, has to get us round in a circle, otherwise the ring won't close. So integral of B dot dl, but that's a piecewise integral because we have regions of no bending, a gap, and then we have a dipole where we have bending. So if we just break this up to piecewise, we have the number of dipoles times its length times some B field seen by the dipole, which has to equal the rigidity times 2 pi. 2 pi p divided by plus q. So I can compute what B field I need for an LHC dipole. This is really an exercise in units. And I've done this so you can ever get confused in a year's time about the units of where the C's should go. Just come back to this kind of example and just see how the C's work. So the B we need is 2 pi times 7,000, 10 to the 9. Then we've got N, we've got L, we've got a factor of C because we need momentum. So there's a factor of C coming in there. Then we've got Q, and that Q cancels that E. And eventually we're left with units of volt per second divided by meters squared, which is a flux density, which is what Tesla is. So we're left with 8.3 Tesla. So that's a pretty strong dipole. So this is what we have in the LHC. And that's why it's in this blue cryostat, because it's superconducting. That's the only way to achieve a field density of that strength. That's a fun little calculation to do. We also need dipoles in other contexts. I wrote these slides a few years ago when I was actually doing LHC optics. So that's why I use LHC as an example a lot. But we need dipoles for other reasons, mainly to find the bending, but also, for example, to manipulate beams. So here we have the region around Atlas. On the left is where Atlas is, and the two beams in the LHC share a common beam pipe, because they have to be colliding, right? They have to be in the same place. In the arc of the LHC, the two beams are not in a common beam pipe. They're separated by about this amount of distance. So we need dipoles not only to define the bending around the LHC, we also need dipoles to separate and recombine the two beams around each experiment. So here's another use of a dipole in the LHC. Here we have quadrupoles, Q1, Q2, Q3, so quadrupole triplet doing focusing in both planes. Then we have dipoles, D1 and D2. And what these guys do is they separate and combine the beams into them shared to a common beam pipe. So we use dipoles in loads of different regions. Ignore the blue and the red. That was some talk I gave a few years ago. I just wanted a picture. That was a talk we gave on designing new collimators for the LHC, where we have existing collimators there, and we proposed a new collimator there in front of Q6 quadrupole to protect it from debris from the collision of the interaction point. You have to decide. Don't worry about that. Okay, so a photocell. So we've already seen that a single quadrupole defocuses horizontally and focuses horizontally, defocuses vertically, or vice versa. But we can combine two together to form a doublet to get focusing in both planes. We saw that before coffee. So the basic building block of any accelerator is what's called the photocell. You may have heard of this already. It's quite a basic thing. But essentially, it's a basic building block of any kind of lattice. There is no Professor Photo, sadly. It's just a nomenclature for a focusing quadrupole, some gap with no focusing, a drift or a dipole, a defocusing quadrupole, and then some gap, which is a dipole or a drift. So the basic building block essentially is this. It's alternating gradient, horizontal for horizontally focusing quadrupoles, spaces, defocusing quadrupoles, and then a space. And we just repeat this, and we repeat this basic cell to make like a repeating structure which has stable beam dynamics. So this is often called a photo channel. So I want to transport my beam from here over to here. I'll build a photo channel of alternating quadrupoles that just keep the beam nicely focused, and it pops out to the side. Quite cheap to do, quite easy to do. Most lattices have a basic photo structure or some variant thereof. So, but note that the drift space, quite confusing, can be nothing, or it can be a bend, it can be some diagnostics, an RF cavity, or even an experiment. So you can put a lot of stuff in these spaces. So the zero can hide quite a lot. The photo refers to the focusing distribution. So the dynamics in a photocell, what we always do, dynamics in a photocell, we compute the one-turn map first and foremost. You always do this. So let's compute the one-turn map, or one-period map rather, of a photocell. Now we know how to do this, right? Because we know the matrix of a quadrupole, of a drift. We just times them together and you get one 2x2 matrix for one pass through one complete cell. And that's our one-turn map, a one-turn matrix. So to do this, we multiply the matrices of the components of the cell together. Now, convention is that we start halfway through a focusing quadrupole. Now, you'll see why in a second. This confused the hell out of me. But you start halfway through a focusing quadrupole. So you have half a quadrupole matrix, a drift, the whole defocusing matrix, a drift, and the other half of the focusing matrix. So you begin and end in the middle of a focusing quadrupole. So we know the matrices. There's the focusing quadrupole matrix, a defocusing quadrupole matrix, and there's a drift. So here's our sequence of matrices. We've got half the focusing quad, drift, defocusing quad, drift, focusing quad. That's the first element seen by the beam. Of course, it's symmetrical here, but it's very important to get your head around the fact that we write the elements right to left in the order seen by the beam. That's how matrices work. So let's be really concrete. Let's take some real numbers. Let's take K to be something. I don't know what. Just some number. It turns out it gives me a stable answer. That's why I picked it. K is, so I want to have a focusing quad where it's going to be plus 0.54. A defocusing quad is going to be minus 0.54. So I've implicitly, slyly made both planes symmetrical. That's very rarely the case, but it just makes them maths easier. A quad length 0.5 meters and interquad distance 2.5 meters. If I just write down these matrices, do the mathematics, I get the matrix for one pass through this photocell. And it's just numbers because I have hard numbers now for my physical quantities. So that's the one-turn map. This is the one-turn map. So we know it must have this form because that's the form of the one-turn map in the current Snyder formalism. See, now it's more numerical, more concrete. So we have loads of information here. We can relate this to this and extract everything we need to know about the photocell in terms of its properties. But really, what we've just done by hand, what an optics code would do. So if you were day one of your job as designing photocells, you'd stick a photocell into MAD, quadrupole, drift, give it some variables, give some numerical values, press compute optics, and it would give you the beta functions and the phase advances. But it's just doing this exact calculation. But codes in our subject were cursed almost by codes. There's loads of them. Everyone handwrites their own code, their own conventions. So be very careful with codes because you never quite know what they're doing. So you should always check the underlying equations. Our subject is bad in the sense that it's a runner code culture sometimes. And that's a very bad thing to do. So you should always check what's going on. So first question, is this photocell stable? I.e., can I just put a beam through it and have it oscillate many times through and just keep going through the same structure time and time again? We know what that means now. We know that's related to the trace of the one-turn map. So we found the one-turn map. We need the trace to be less or equal to 2, the mod of the trace. Our trace is 1.415. So that this gives you stable motion, i.e. it's got a real phase advance. What is the phase advance? Well, the phase advance is just simply arc cos of half the trace. So if you do the calculation, we get 45 degrees. So the phase advance in each plane is 45 degrees, a betatron phase advance for one trip through the photocell. So our betatron function, beta, advances by a phase of 45 degrees. So the jargon for that is it's a 45-degree cell. When people say it's a 90-degree cell, they mean the phase advance in a given plane is a certain number of degrees. What are the lattice functions at the point of the one-turn map, in the middle of our F quad? Well, we know this because we know these expressions from our current styler analysis. So we know beta is just m12 over sine of psi. We know psi now, and also we know alpha is given by the difference of these elements divided by 2 sine phi. So this is what Mad's doing. We do it by hand. We calculate that. We find that beta is 11.6 meters. Great, it's positive. Units of meters is telling us the maximum amplitude a particle can go to. And alpha is 0, interestingly. Alpha is the difference of the unideal elements. So we just go back to our matrix. You see, they're the same, so alpha is 0. Think of the ellipse again. Alpha was the amount of ellipseness. It was the cross xx prime term. So alpha being 0 means that the ellipse is actually a circle at that point. And it turns out that the turning points of beta are actually in the quadrupoles, which means that the ellipse will have a circle in the middle of the two quadrupoles. That's why we pick half the focusing quad to start the calculation at. If we picked the calculation a full focusing quad back around the same point, that wouldn't be 0 alpha because we wouldn't have a symmetry point. So that's why we do it. So what does MAD compute? Well, you can download it for a Mac or for Windows. If you haven't tried it MAD before, download it, learn the syntax. Like an 8-line file will give you this lattice. Compute beta, everything. It'll all come out. It'll come out pretty accurately. We are also going to do more stuff, and what we're doing now is not just being perverse and just doing the calculation in loads of different ways. We're trying to get insight out, because accelerator physicists, we have an underlying theory, but often in the control room we haven't got time to sit down and calculate some beam dynamics. We want intuition about our accelerators, and we're starting to get this by doing this kind of calculation. So let's compute the same stuff in the thin lens approximation. So let's do this again, same calculation. So here we have, from the middle of the QF, we've got half the QF, drift, QD, drift, half the QF. Multiply those guys together, and we get this. Now it's parameterized in terms of L and the focal length F, and it looks a bit like that. There's loads of information there, and I haven't got time to discuss all the information that's in there, but for example, what range of L and F gives you a stable motion? That's a question to ask, and actually you're going to learn something about beams a lot when you do this. You need a trace of this guy less than 2, or you need mod F greater than half the drift length in your photocell. Also, we can write the phase advance in terms of the cell parameters. The cos of the phase advance is 1 minus L squared over 2 F squared. So you can do that, and I'm just pointing out you can do that, but there's an interesting lesson here. Looks a bit weird, that. Stable motion means the focal length has to be greater than the drift length over 2. That's necessarily not sufficient condition for stable motion. What it seems to say is that motion is stable when focusing is weak. That's what it seems to say, because the focal length has to be bigger. This is how a long focal length is a weaker lens. Stable motion is when this tends to be weaker. Now, so a bit of philosophy for you, that often your first thought is when you fire up MAD, you whack the quadrupole strength to try to get some stable motion, and this just doesn't work. And this is the reason why. Strong quads aren't better. Beams like to be massaged into nice stable motion, and you achieve this by roughly getting, a good rule of thumb is focal lengths of the order of L or half L over 2, something like this, and that's your starting point. And you can see why. Here we have a focusing quadrupole, and remember the amount of the angle change is proportional to your distance off axis. Remember that, that's how our linear approximation that we had. So we have some focusing here, that's a fairly weak quadrupole, so that's done nothing there, but this strong quad has pushed us beyond the bounds of this, and we can't recover the motion. So what stable means is that the position of the particle is being pushed to larger and larger positions, turn after turn after turn after turn, and these strong quads are doing that. So that's a good bit of that intuition building there in how to design lattices. A good starting point for codes, like I say, is to make the focal length, compute it by hand on a calculator by MAD, and then have your initial conditions before you start searching in your code for what your strength should be, is to have this condition obeyed exactly. That's a good intuition. Your intermagnet drifts should be roughly the order of the focal length of your magnets. That's what you typically find in lattices. That's a good place to start. Well, what's the beta in our photocell? We know the phase advance. We can now find betas. We just use these equations again. So the betas in the focusing and defocus controls are maximized, and this maximum depends only on the cell length and the phase advance. So if I just use my one-turn map in terms of L and F, apply these equations, I find that the beta in the focusing quadrupole is given by this, alpha is given by naught, and gamma is given by that. In the D quad, F just goes to minus F, so I find the beta in the D quad is simply given by that. So there we go. So you can just play with these equations and you can calculate the motion in your photocell. Now here's the question. So here's the beta functions. I forget, if it's these examples or not. I can't remember if the numbers are the same. Pretend they are for a second. That's the focusing quadrupole, that's the defocusing quadrupole. You see that beta x is maximized there, and it peaks every time in the focusing quad, and vice versa for the other beta function. So here's a question for you. That's the beta function expressions in the middle of F and D quads. How would you compute the beta function anywhere in the photocell? So how would you calculate the evolution of beta through the whole cell? So that point, that point, that point, that point. You have the equations for that now. And what about expressions for the maximum and minimum beta function in the cell in terms of length and phase? These are not in terms of phase, these are in terms of F and L. What's the maximum in terms of the phase? That's another good thing to do. Oh, another exercise. So we've got a photocell where the focal lengths were the same. We picked K plus and minus something or other in the two quads. We got 45 degrees phase advance in both planes. Imagine they were different. What would this mean about the phase advance in the two planes? Then assuming a thin lens code, find the phase advance at each plane for a focusing quadrupole with focal length F1 and minus F2. So that's a fun exercise to do. Optional, obviously. So here's a real photocell from a real accelerator. Again, I picked the LHC, but it's just a synchrotron, any circular accelerator. It's actually, so here's the cell. It's a photocell. It's 110 meters long. There's the F quad. There's the D quad. There's the F quad. So we have this F0, D0 structure. In the LHC's case, the quads are a few meters long, so the O's, the gaps are really quite big in the LHC. And the reason for that is we have to stick all these dipoles in. So we stick 3 dipoles in each interquad distance. So that's 3 times 15 meters. That takes up most of the space. Then there's some diagnostics, and mostly it's taken up by what's called corrector magnets to correct the orbit, correct the beta function, correct the higher order behavior. There's more on that later. So that's a real photocell in the LHC. We just build the LHC out of loads of photocells, and here's the beta functions. So you can see I've started the calculation slightly at the end of the focusing quadrupole, so I maximize beta x and I minimize beta y, and then beta y peaks in the horizontally defocusing quadrupole. So there's 110 meters long, and the betas go from 38 all the way to 190 odd. So that's quite nice. It's a 90-degree phase advance in both planes. So I could build the LHC. Imagine you're building the LHC. Right, that's your job. You understand the photocells. You can make a stable optics. You can stick loads of dipoles inside the gaps between your quadrupoles. You can make a beautiful ring made of photocells. That's great. As a beam physicist, you can go home now. But however, Atlas's CMS can be well grumpy because there's no space for their detectors. What you need is you then need to break the symmetry of your repeating photocells and have long drift regions to put things like experiments in. So what if we can build our ring from dipoles and photocells. What about a region free of magnets to put something massive in, like a detector that's like plus or minus 20 meters? We have to start focusing for a while. So what's going to happen? Well, if you go back to the expression we had just before the break, where we computed the beta function at a point based on beta function at a different point, the expression would look like this if you just had a drift space. So I'll leave deriving that as an exercise for you. But you just use the expressions we had right at the end. It was a 3x3 matrix of like beta at 1 in terms of beta at 0 in terms of M11, that kind of thing. You know M for a drift of length L, stick the expressions in, you derive this. But that's for fun. One Saturday night you can do that. But now look at the answer. So if we have a drift, we have some beta function at some observation point. This is how it evolves. So what happens to our beta function in a drift around a symmetry point? Well, at a symmetry point, here's the LHC. There's the interaction point where beta is minimized, so alpha is 0. So we can cross off this term. Then we have the drift before the first magnet. This says that the beta function, if that term's gone, will be proportional to L squared. So the beta function will rise quadratically in a drift around a symmetry point where alpha is 0. So in a drift space around a symmetry point, the beta function rises quadratically with distance from the symmetry point. Well, this is what I've just said. So if alpha is 0, we have gamma is 1 over beta. So the beta function around a symmetry point goes as the beta function at the symmetry point plus s squared divided by beta naught at the symmetry point. So the point of all that is that beta functions in drifts rise very rapidly if we're not careful. So this is very bad for accelerator designers. Now, what happens can be done in terms of an ellipse. The area of the ellipse is constant. So if I want to squeeze beta down to a very small point, say at an interaction point in the middle of my drift, my magnet-free region, I get a very, very squeezed beta, which means gamma gets very, very big if you go back to your ellipse equations from before coffee. So remember what gamma was doing for us. Gamma was the projection of the ellipse onto the y-axis, i.e. that's the divergence of the beam. So small beta, big gamma, beam rapidly expanding in terms of transverse size. So the LHC, we see that. So about the LHC, at this point here, alpha is 0, beta is 1 over gamma, then the beta function rises quadratically as we go away from the into the drift. So this is well bad for us because we don't like big beta functions for many reasons. And it's also an example of Liouville's theorem, which states that the area occupied by a beam in phase space is constant. So that's the formal statement of our admittance area is constant. What it means is if I push, imagine my beam is jelly in phase space. If I push it down so it's got a very, very small position projection, it squidges up the y-axis, giving me a very, very large angular projection. So I get a very angular divergent beam. So if I squidge something down so it's got a very, very low angular divergence, it gets very big physically in position space. So this is an example of Liouville's theorem, which is all to do with the area of the ellipse is constant, but I can manipulate the shape of the ellipse. I won't have time to really discuss this in great detail, but if you hear Liouville's theorem, it's probably the most important theorem that we have in accelerator physics, and is really linked to this conserved ellipse area that I've talked about. Now, what we call this is a mini beta insertion. So this is the region around Atlas. That's the drift we've generated to stick the detector in. We get beta as small as possible to decrease the beam size, therefore have more interactions per second into Atlas. We have, as a point of minimum beta, alpha is 0. We call that a special thing in this subject. We call it a beam waist because it narrows to a minimum. And we have this quadratic rise of the beta function coming away from the beam waist. So we call this arrangement of optics in a drift region to minimize the beta function a mini beta. It's called a mini beta principle sometimes, but that's just a fancy word for something that's fairly obvious from our equations. So you can now start to understand the LHC optics in great detail. LHC is made, it's a big ring. We have to get the beam round, we have to bend it. So we use photocells. So we have alternating gradients, the gaps of which are full of our dipoles. We know that's 8.3 Tesla. We can find some parameters in MAD that give you stable motion in both planes. 110 meter long photocell, periodic betas. That's what we see here. So that's our photocell structure. We could build the ring so we're bending in this region. We could build a whole ring of them, but there'd be no space for the experiment. So we have a focusing free region. We have to accept the beta will rise very large when we do this because of this L squared dependence of the beta rise. So we say, let's have a detector there. Alpha is 0, it's a minimum. Beta is really small, fixed by the physics requirements. Beta then rises quadratically, very high. We then catch it in some focusing quadrupoles to turn it back over. Then we've got the beta here, the beta here. We have to make them join up, it's a continuous function. We stick some extra quads in here to match the periodic solution into our mini beta solution. And that basically is how you design the LHC, with a few extra complexities on top. That's a basic linear idea. So that's really bad. This beta is massive here. Now that beta is related to the maximum amplitude a particle can oscillate to. Remember our coincider ansatz. So big betas here means our beam size is very, very big there. And also we need strong quadrupoles to focus beta back around to a minimum. So we need strong, large aperture quadrupoles. So if you go to any meter of the LHC now for the upgrade, half the effort is making the quadrupoles as strong as possible for this exact reason. So that's the challenge. So large betas, big beam sizes, big aperture magnets. That's a problem. There's also a second problem to do with errors, which we'll hear about in a second, but big betas generally are a bad thing. So I put on here some lattice design stuff. I won't go through every single one, but this is a flowchart, if you like, of designing a lattice and an accelerator. So it takes a long time to do. It's an iterative process involving users. What requirements do they have? Funding, accelerator physics, where your RF goes, where your diagnostics goes. You start with big parameters, energy, size, LHC, 7 TeV per beam. The tunnel was given to us by LEP, so we couldn't do much about that. You work on diamond and RAL, you have a certain constraint on the building size. You then build the linear lattice. Your energy and size determine your dipole strength, approximately. You then have to make a linear lattice. So this is where the quadrupoles go, what the beta functions are, what the tunes are, what the apertures are, all this kind of stuff. And that's a lot of work there. You use some code, MAD, beta, elegant, Tracy, there's billions of them. And what they essentially do is what we've done by hand. They match lattice functions, they calculate apertures, they look at stability. Usually you have periodic cell structure in a circular machine and a linear machine, to be fair, and you have a whole bunch of building blocks. A photocell is our basic building block we've studied so far. There's loads of others, but I can't tell you what these are until we've studied dispersion in 3 weeks' time. So we'll come back to this slide and look at it again once we've understood dispersion. But we've understood a cell could be photo. But you can understand the LHC structure now. It's a photo arrangement. Number 6 I put on, but nowadays you'd mostly consider separated function magnets, so quadrupoles just are quadrupoles, dipoles are just the dipoles. You then have to worry about the maximum field strengths, apertures. Then you have to worry about an insertion. An insertion was like our mini beta for the Atlas experiment. It's a bit where we do something special with the beam for a certain purpose. So here, in the LHC example, we match the beta functions down to a small point inside of Atlas for a very, very high collision rate. In Diamond, you would have insertions to insert wigglers and undulators to generate synchrotron radiation light. So once you've got your basic ring, you stick extra bits in. I put these 3 in little, because once you've studied more things about sextupoles in 3 weeks' time, I can explain the last 3 steps to get your basic lattice sorted out. And I think I've shown you this slide before, haven't I? So we'll skip that. And that one, we'll skip that one as well. So that's the basic of lattice design. Before we go on to the next level of lattice design, sextupoles and achromatic structures, we have to have a little interlude to worry about real life, sadly. As an accelerator designer, you have to actually build your accelerator. And I first studied this subject. And my first ever course has all beta functions and lattice design. Suddenly he was talking about errors. And I was like, well, that's a bit boring, isn't it? You know, that's just like... But then I realised that ours is an applied subject. And if you design an accelerator, when you build it, the positions of the magnets and the strengths of the magnets will not be what you think they are. And we are surprisingly sensitive to this. So this is a very important topic for us. So now we're going to have a sort of 20 minutes or so on that's our ideal photocell. In reality, it's misaligned. In reality, the power supply gives you a strength ripple. What does that do to our beam? So that's what we're going to talk about now, errors and misalignments. So real life has got in the way now. It has got in the way once already because we designed the LHC out of lovely photocells. Then Atlas came along and said, I need like 40 meters to put my detector in. So you have to have an insertion. Real life accelerator designer is errors and misalignments. So recall ages ago we had an arbitrary vertically pointing magnetic field, BZ is a function of X, and we made this multipole expansion. This bit is the constant bit, the dipole bit. That was our quadrupole, our linear bit. Then we have this higher order terms, sextupole, octupole, and so on and so forth. The first bit does the steering. The second bit, the quadrupole bit, the KX, does the focusing. The third bit will do other stuff we'll see in 3 weeks' time. But we then have to build these things. And we build them, we have to specify some how good the field is. Because I say to someone in the magnet group, I want a quadrupole of this strength. I don't get a quadrupole of that strength. I get something that's pretty damn close, but it's not perfect. So as well as specifying a strength, like the value of a K, I have to specify how accurate I need that K to be. And that comes to the beam dynamics. As a rule of thumb, for modern synchrotrons, we tend to look at 1 part in 10 to the 4 for the accuracy of fields, accuracy of gradients, accuracy of dipoles. So magnets mostly have the component you want, but will have some contributions from other orders of component. So for example, I would have, for example, extra higher order terms in my ideal quadrupole. So I need to have a formalism to understand the impact of these on the beam. I also have to have magnets in the right place. So if I have a quadrupole and I whack it in the beam line, but I have it slightly off-center transversely, it's going to generate an additional dipole field on the beam. Perhaps you can see that just from your head, or you can just show it mathematically by doing a transformation x going to x plus some offset. So if I have an offset quadrupole, I generate an extra dipole field. What does that do to the beam? Or a power supply is not quite right. It's giving me a wrong current into a quadrupole, changing its K value. So the bottom line is our lattice is never as we think it is, ever. And we have to deal with these field errors right from the start. So there's a few results we have to do. And to see what kind of happens, imagine we have a stray dipole field, or we have a misaligned quadrupole. This will generate a dipole field. This will kick the beam. And here we have our ideal reference orbit, this black thing here. And at this point, we have some additional dipole kick. So I get some extra angle on a particle. This will then come up and it will start to oscillate around the machine. So what we'll see that when we have these dipole kicks and such things, we actually get oscillating offsets of quantities around the ring. And the rate at which they oscillate, how fast they oscillate, varies depending on what kind of kick you've just had. Oops, well, it's back. I don't know what happened there. Right, so our first topic is what's called closed orbit distortion, or COD, if you want to call it like that. So the design orbit of an accelerator is defined by all the dipoles in the ring. This reference trajectory defined by the dipoles is called the closed design orbit. Orbit, it's a trajectory around the ring, particles oscillate around. It's closed, it joins up on itself because that's how we design it, and it's designed as we designed it. That's the perfect situation. Now imagine you have a small dipole kick. This orbit will distort slightly, and the distortion will run around the entire ring. So if I have a small kick in my accelerator, any location, just one location, I'll see the effect of it around the entire ring as the kick oscillates around the ring, because we have a periodic focusing. So here's an example. Here we have some beamline Red denotes the Beatron envelope, the maximum value of the transverse oscillations, the Beatron oscillations. Here, blue is our ideal design orbit. And then here we have some green, which is real. At this point here, there's a stray dipole field. It kicks the beam, and this then starts to oscillate up and down around the ideal design orbit. This is called closed orbit distortion, COD. And there's a whole, people have jobs on COD and in synchrotrons, correcting it and measuring it. So the orbit distortion defines a position-dependent orbit offset around the ring. In effect, particles oscillate around the design orbit, but around some new closed orbit. So what that means is, think what we did, right? We had dipoles, and they defined a closed orbit around the accelerator. We then expanded Hill's equations around that design orbit. So our Beatron oscillations were around some ideal design orbit. This kick is going to shift the orbit around which we're oscillating by a constant, by a certain way around the entire ring. So in some sense, our position of our particle is now a oscillating component, the Beatron oscillation, plus a shift. And this shift depends on S, because this shift oscillates around the ring, and it's called the closed orbit distortion. So the motion of the particle before had one bit, its oscillation around the ideal orbit. Now we've got oscillations around the ideal orbit added plus an extra shift from the distortion of the ideal orbit. See what I mean? I know it's quite funny. This closed orbit has a periodicity of the ring. It has to, because it repeats on itself. So imagine we have some dipole kick error at some location S0. So you have some bad extra dipole field, call it delta By, and it has some length. So the integrated strength is delta By times L. I'll normalize that as beam rigidity, because that's what we always do. And that actually gives you the angle kick seen by the beam because of that stray field. I can go away and I can calculate this. I'm not going to calculate it for you here and now, because it takes like 15 minutes and we don't learn any more physics by it. I will look at the answer. The closed orbit distortion, i.e. the offset to my normal Beatron oscillations, is a function of S, because of course it is, and it's given by this. So this is the bit I offset my normal oscillations by around the ring because of this single error. It looks like this. It's proportional to theta. It's proportional, strength of the kick. It's proportional to the root of the beta at the point I'm observing. So I'm interested, how big is the offset at this point? It's proportional to the root of the beta there. It's also proportional to the root of the beta where the dipole kick error is. So I get bigger orbit distortions if I have errors in places of large beta functions. So the beta function is now telling us something new. Before, it was telling us the maximum oscillation of a particle. It's now telling us how sensitive my beam is to errors and misalignments. That's new information. The beta function is really good. It's full of stuff. So it's telling us my distortion to my orbit is proportional to the root of the beta function where the error is. So the beta function is my sensitivity factor as well. So beta function has lots of stuff in it. Times by an oscillating bit. So this is oscillating at pi times the tune of the whole ring. That's what nu is, that's the tune. Minus the phase difference between the phase at the kicking point and the observation point. Notice this is cosine of this. So this phase difference is how fast the beta function oscillates at. This function oscillates at the same frequency as the Beatron function. That will always be the case, as we'll see very shortly. So here's an example. Pink is a Beatron oscillation. So that's my accelerator. I've got oscillations around some reference trajectory. Then I kick the beam at one single point, and I see this new blue oscillation. So this blue is composed of this pink bit plus this function here, which is oscillating around the ring proportional to my kick. And notice these things are perfectly in phase. So the oscillation frequency of my offset is the same as the Betatron oscillation frequency of the pink before I had the kick. Finally, there's this bit here. I think I've got a slide on this. Yeah. So all the anatomy of that expression is interesting. There's physics everywhere. But also there's an overall factor in the closed orbit distortion of 1 over sine pi times nu, where nu is the tune of the machine. So this means every time the tune is integer, 1, say, in units of 2 pi, the argument of the sine becomes a multiple of pi. So sine of pi is 0. So I get 1 over 0. So this diverges. Every time the tune, nu, is an integer, I get a divergence in this closed orbit distortion. That's our first example of a resonance. So let's be concrete. If nu was 2, so the tune was 2 in units of 2 pi, that means I have sine of 2 pi, sorry. So I'd have 0. 1 over 0 diverges. So this offset to my Beatron oscillations from the single dipole kick appears to get really big if the tune approaches an integer. So the closed orbit distortion gets very large, and that's an example of a resonance. So imagine I built an accelerator. I went upstairs, I designed it. My one turn phase advance was 2 pi. Okay? Bad choice. You think, well, why not? Just a nice oscillation. So if I had even a single dipole error in that accelerator, it means the beam would encounter that dipole error every turn after turn at the same point in its Beatron phase, the same point in its motion. So the effect would add constructively, turn after turn after turn after turn, and drive it to very, very large transverse amplitude. That's physically what happens. Mathematically what happens is this guy here diverges. So the effect of the dipole error adds up turn after turn after turn after turn. So we never design accelerators to have an integer tune, because even a single dipole error, I'd lose the beam straight away. So the tune choice is critical to do with tolerance to misalignments. So we've learned from here, we should, to minimize sensitivity to magnet errors, we should stay away from bad values of the machine tune. Here, an integer is bad. 2 pi, 4 pi, 6 pi, 8 pi. So that's what we learned. What we're going to see is that's an example. That's an easy example of resonance to come across. There are resonances at many, many other tune values. We'll see in 3 weeks' time we have to avoid half-integer tune values because of quadrupole errors and so on and so forth. So there's a whole slew of possible resonances that generate large amplitude behavior from our particles. And in fact, generally, I won't derive this, but I just want to see it. Generally, a bad resonance occurs when the horizontal tune times some integer plus the vertical tune times some integer equals some integer. That's a general resonance condition. And the order of the resonance is given by the sum of n plus n. See, then you think, well, hang on. What values of the tune am I allowed to have? Because I must always satisfy this, because some choice of m, n, and p. There must always be some resonance being driven in my accelerator. And that's true. And as you learn about accelerators, you'll reach a point of understanding, hopefully now, but if not, you think about it. You think, how the hell do accelerators ever work? Because I can never avoid tune points in x and y that don't satisfy this condition for some choice of m, n, and p. How do you ever make an accelerator work? You always have resonances driven that can make you lose the beam. And once you sort of appreciate that fact, you start to learn about beam dynamics a little bit. And the answer is, I'll tell you so that I'm not upset in case you think nothing works, is because the higher m and n get, the impact gets less and less on the beam. So we're always close to resonance at some 56th order. But the higher the order of the resonance, the less impact it has. So this resonance here is what's called a first order resonance, integer tune. That'll kill you. You can't be near that. A second order, half integer tune, that kind of thing. But you're always near something. LHC tune, we're clear of resonances that I think 10th or 11th order. After that, we just can't do it. But that's high enough order that the impact on the beam is sufficiently small. But really, mathematically, accelerators never should work because of this resonance condition. That's an interesting fact. If one thing you remember today, remember that. Right, we've got 5 more minutes. We'll just do quadrupole errors. I'll rush through it. So we've just had an extra dipole error. Imagine we had an extra quadrupole error. An extra quadrupole was there. The field was slightly wrong. Something like this. This would have 2 effects in our picture. The first, quadrupole, different K, the tune will change because the Ks are different. And also, the beta function will change as well. And there are 2 effects we have to worry about. Let's calculate it. I've done this explicitly because it's a much shorter calculation. So imagine we have some lovely lattice. We have some quadrupole error in the lattice which has some strength plus Q. Right, let's compute it. Because this gives you essentially a thin lens extra matrix in your lattice that looks like this. It's a thin lens quad matrix, 0, 0, Q some positive number. So that's essentially the thin lens kick giving you 1 over the focal length. Right there. So that's the number. So that's the extra matrix you have to worry about, where that's some small quantity. The rest of the machine you can represent easily as a one-turn map. That gives you the whole machine in one little object. So I can find the global dynamics impact by having my one-turn map. So that's just the map for one turn. Now I have one turn quadrupole kick, one turn quadrupole kick for turn after turn. So the new one-turn map is that times that. That's the new one-turn map, if you see what I mean. And that equals the new one-turn map. So we calculate it. If you multiply those 2 things together, it's 2 lines, 3 lines. You get this, where this is the new one-turn map. Notice it now depends on the old lattice quantities, but also it depends now on Q, our extra little quadrupole error. So if Q goes to 0, I should recover what I should get the right answer. This is the perturbed one-turn map, i.e. Q is small, so I'm doing a perturbation theory calculation. What's the perturbation on the one-turn map? So 0 will always represent the unperturbed machine quantities, beta, phase advance, that kind of thing. And the subscript P will be the perturbed machine with the extra quadrupole field. This new perturbed machine has its own one-turn map, given by that, where that's a new tune, that's a new beta, that's a new gamma, so on and so forth. See what I mean, what I've done there? So I can figure out the new tune, because tune is linked to the trace of these matrices. So because this is in terms of, that's with the perturbation, and that's the parameterized new perturbed one-turn map, I can equate the trace of that to the trace of that, to link the 2 quantities together. If I do that, I get this expression, which links the new tune to the old tune and Q, which relates the unperturbed tune, new. There should be a 0 there, I guess. Okay, yeah. And that's the tune for the perturbed machine. If Q is small, the tunes are close to each other. It's a small perturbation. I'm shifting it slightly by the quadrupole map. So let's assume it's small, and I'll do a linear expansion. So the perturbed tune is equal to the unperturbed tune plus some small shift. It's a small quadrupole field. I can then expand my cosine functions. I've got, if I have cos of this guy, I can expand it like this. I put the full equations there, but I won't go through them in detail. I can then, because I have things like that, dv is small, so cos of something small is just equal to 1. Sine of something small is, sine x goes like x for small x, so I can approximate sine by that. I arrive at that. I cancel some stuff. You can do it on Saturday night if you want to. And I arrive at this formula. So this formula is telling me the shift in the tune in my lattice for a quadrupole error at some location which has a beta function, beta naught. So note straight away that in the linear approximation, the tune shift is proportional to the quadrupole error. It's also proportional to the beta function. So as we saw for closed orbit distortion, the shift in the orbit proportional to the root of the beta function. The shift in the tune is proportional to the beta function at the point where the extra quadrupole field's coming in. So a big beta function big sensitivity to the tune to quadrupole errors. That's the message. So I arrive at this formula. The tune shift is the perturbed tune minus the unperturbed tune is given by plus Q, the quadrupole field, times the beta, where this error is at, divided by 4 pi. That's a well-important expression. So, tune shifts. This is, what's the next slide? 2 more slides and we'll stop. So, tune shifts. Lattices have straight quadrupole fields. The shift in the tune to the quadrupole error Q is given by that expression there. So, here's the following important features. The perturbed tune increases if the quadrupole field strength is greater than 0. Makes sense, right? Because positive Q is more focusing in that plane. I'm focusing tighter. I do more oscillations for a given turn. So the tune should go up. So a quadrupole field would shift the tune one way in one plane and another way in the other plane, because there's just different Q in the 2 planes for a quadrupole. However, we also get tune shifts and other effects. Space charge, beam, electron cloud. And here, the effect of the quadrupole error is proportional to the local beta function. So beta functions are telling my sensitivity to field errors in my lattice. If I have lots of quadrupole errors, I can just turn it into an integral, so I get a little tune shift from each of the errors. So I just have an integral around my ring, ds. K is some additional quadrupole strength at the position S. Beta is the local beta function. I integrate around the ring, product of Ks and betas, normalized to 4 pi, and this gives you my tune shift. So that's a very, very important expression. It's also used to measure beta functions, because if I artificially change the K of a magnet at some point, and measure the tune, the amount of tune change is proportional to the local beta function. So I can measure beta functions this way as well. So in general, a beta function tells us how sensitive we are to perturbations. So for example, the LHC, we have large beta functions in the ring, bigger than we had in the upgraded machine, has bigger beta functions in the old machine, so we're much more sensitive to field errors. And what's next? Beta beat. 2 more slides, and then I can start a whole new section next week. So 3 weeks time. So that was quadrupole comes in, you change the tune. You also change the beta function, because that also depends on the quadrupole distribution. What happens to the beta functions around my ring if I have a quadrupole error? So I'll skip the derivation. It's short, standard in any accelerated physics textbook. The change in the beta function around the ring, because of quadrupole error, is something called the beta beat. It's the beating of the beta function away from its nominal value around the ring. A good quiz is why it's called beta beating. Okay, I've told you on the slide. So here's the expression for the beta function. Again, we have proportional to the local beta, proportional to Q. We have a resonance condition, but now it's 2 pi nu, so we have to avoid half-integer resonances of the tune. We also have this oscillation around the ring, but notice it now is a factor of 2 there. So the oscillation rate of a beta beat is twice that of the betatron function. So that's characteristic of a beta beat. That's why it's called a beta beat, because beating happens at twice the frequency difference between 2 coherent sources. So that's called a beta beat. We get a beta wave around the ring that oscillates at twice the betatron frequency. And the strength is proportional to the quad error, but also the beta function to the first power at the point of the quad error. And notice the sine 2 pi nu term. This is expression every time that nu goes a half integer, we're going to get a big resonance effect. So we've seen resonance twice now. Tunes integer from quad errors and half integer from quadrupole errors. You can see what's going to happen, right? Sextupole is going to be as you would expect. And finally, here's a measurement of beta beat. LHC, you've seen this plot before, position versus beta beat around the ring in the 2 planes. So in the LHC, there's hundreds of magnets. All of them, most of them have an extra quad field, so that all these beta beats add up around the whole 27 kilometers. So it's pretty remarkable that I have to integrate around every single quadrupole error times massive beta functions in places, but I still get an integrated effect of only 20% around the whole ring. That's why that's a world record for a proton machine beta beat. Right, I've overrun, sorry about that. So there's nothing next week, and then there's other people doing stuff. I don't know what the schedule is, but I think we have to come back in 3 weeks' time
where we'll talk about off-momentum particles, dispersion, chromaticity, lattice design, and also longitudinal motion in cavities. So thanks very much.